Let's say we have this situation that's similar to dart throwing. What we're interested in is how close we are to the bullseye, the exact bullseye. We're interested in our miss distance from the center. So you can ignore the numbers around the outside and the double and triple values. Just how close to the bullseye are we going to get? We're ultimately interested in that as a probability distribution. Probability distribution of our miss distance. Well, we're willing to make some assumptions to get a handle on things. Overlay a little coordinate system. So we have X meaning the horizontal miss distance, and Y is the vertical miss distance. And we'll assume that each one of those has a Gaussian distribution, a good old bell-shaped curve, normal distribution. And we'll assume zero mean, so that little bell-shaped curve peaks right at the middle here. And we'll make even more assumptions. We'll assume that both those Gaussian errors have the same variance, the same standard deviation. And we'll assume they're statistically independent. That's a lot of assumptions, and I'll talk about assumptions later. But we have two random variables here that we're willing to make assumptions about. We're interested in other random variables, namely the miss distance, how far away from the exact bullseye, and while we're at it, the angle of the miss. We're called straight out here is angle 0, and it goes all the way around 2 pi. So there's 0, there's 90 degrees, or pi over 2. There's 180 or pi, etc. The situation we have here is we have variables over here, this distance and angle, that are functions of these two other variables. So we have these guys' distributions. We want these guys' distribution. We go about that in general. So we have, say, X and Y, two random variables, and we have this other random variable that's a function of those. Well, the definition of the cumulative distribution function of a random variable, we'll call that uppercase F here, of Z, is this probability. That's a definition. Probability of the random variable is less than or equal to some argument you give it. And in this case, you plug in this function. So that becomes this probability. How do you find the probability that some function of two random variables obeys some condition you give it? You integrate the joint probability density function of those two random variables over the region where the condition is true. Region of integration is the big idea. And then once you have the CDF, the cumulative distribution function, PDF, or the probability density function, just the derivative of the PDF. Okay, so where do we get this joint PDF? Because we started out with two individual PDFs on X and Y. But we said they're independent, so the joint PDF is just the product of the individual PDFs. Here's the PDF of X, here's the PDF of Y, multiply them together, rid of the square root, that becomes a sigma squared, and the exponents add. So this is our joint PDF. It's going to look like this. Region of integration is some region in this XY plane, and we find the volume under the surface. What we're doing. Get into applying that to miss distance and angle in the next video.